Okay, so here we go. Last time we were talking about these physical examples. Let me just hit some very broad highlights first. In our first physical example here, we're talking about a light bulb. A light bulb creates the flow of a fluid, namely the fluid is that of photons, right? Those are the particles making up the fluid. Some particulars about this fluid. It is being generated in the example, right? The fluid there's not any sort of limits on how much of the fluid there is. It's being consistently generated through time in the example. However, the density never changes. Right now, there's greater density closer to the light source. There's lower density farther from the light source. Yeah. But in terms of time, as time passes, none of those densities change. Okay, quite the opposite for this other example. In this other example, we had a finite amount of gas, and we're the gas is expanding outward as described by this vector field. I made a metaphor of a balloon, right? It's an expanding balloon. The gas kind of expands with it. So quite the opposite. There's no fluid being created here. There's no generation of fluid, right? Unlike the photons. And then, however, also in contrast, the density here is changing, right? The fluid density is not constant. It's not independent of time. It does change. Okay, so we get different interpretations of flux and therefore different interpretations of divergence because of, they're different kinds of fluids and we have to interpret differently. So I want to point out real quick that sometimes you can have both of these kind of phenomena happening at the same time. So you could have a fluid flowing where there is, on the one hand, fluid being generated, but there might also be collections, the density might be in the process of increasing or decreasing. Both can be the case. In some sense, these two examples here are two extremes of a spectrum, right? And you can have something in between. So, here's an equation that I like to relate all of the objects in play. I think this is a good starting point. Let's suppose that you do have fluid being generated at a certain rate. And I propose that there's really only two possibilities of what can happen with that fluid that is being generated. Either that generated fluid leaves your surface, leaves your given, bounded region through the boundary surface, in which case it contributes to flux. The other possibility is that it does not leave, and if it does not leave, then it contributes to the collection of fluid in your region, right? So either it leaves or it doesn't leave. And writing that down, you get this equation. So it's a short step then to divide by volume and take a limit, right? So differentially per unit volume, as I like to say. What is flux per unit volume? That's divergence. That's our primary interpretation of divergence. Mass per unit volume is density. And now this thing on the right, this is a new kind of unfamiliar concept. Generation rate refers to how much total fluid per unit time is being computed overall over the entire region. Dividing by volume gives us this idea I'm calling generation rate density, by which I just mean how much fluid per unit time is being created per unit volume in a vicinity of wherever you might be looking. So what we get then is a relationship between divergence, which is something that you can compute, and these two sort of more physical quantities that are going to depend on the particulars of the question. Okay, so I just wanted to point out that you can interpret divergence when you have one of these kind of hybrid fluids, depending on what the circumstance is. And this is not a physics class or an engineering class, so those circumstances will arise in your other classes. Okay, so moving along, I want to talk about some more physical examples. Gravitational fields is going to be my next example, and y'all probably y'all have definitely seen this before. Point mass creates this gravitational field, we call it. Right? So we saw this back in chapter 3 as an example of a inverse square radial vector field. Okay. Real quick observation. This assumes you have a single point mass. That's not a physical real thing. There's no such thing as a single point mass. But it is a fantastic approximation of a legitimately real thing, which is you can talk about the gravitational field created by a teeny tiny little thing, even if it's not purely a geometric point. Okay. Neat observation to make about this vector field, this inverse square radial vector field. I didn't make this observation back in chapter 3, but it's very useful here, and that is, it is just like the vector field for a point light source. It's radially outward, right? And as you would naturally expect, point light sources seem brighter when you're closer, right? They're dimmer the farther you are away, and it turns out they're inverse square in that sense. So this is a real eyebrow raiser. It's very strange that these two very different physical scenarios, light being created by a light bulb, gravity being created by a mass, would have exactly the same vector field up to a constant factor, right? So highly suspicious. So when stuff like this happens, it is reasonable to speculate on hey, maybe this is not a coincidence. Maybe these are literally the same things happening in different particulars, of course, but they may be more closely related than we think. And along those lines, there is a theory that gravity is kind of like light in that it is communicated by emitted particles created by, well, not a light bulb, right? Photons are created by a light bulb, but the little emitted particles here created by the mass. This would be the analogous thing, right? So, this is a theory. They call these little emitted particles gravitons. And now, do gravitons actually exist? Well, a long conversation ensues. Ask a physicist. You'll see what I mean. It's a very long, complicated conversation. I throw up my hands and say, it doesn't really matter. That's not what we're here for, right? The point to be taken away here is that you can think of gravity this way. It doesn't matter if that's physical or not, right? The point is, if you were to pretend that it is, then you would get the exact right vector field. It behaves exactly as if there are gravitons. So let's go ahead and pretend that there are, and whether there are or not is somebody else's problem. Right? This will not lead us astray because the algebra works out exactly right. So this is a really nice way to think about gravity. It allows you to think about things a certain way. So here we go. Let's talk about all of this algebra in here. I'm going to come at this bit by bit. I'm going to start off with the simple observation that mass is a triple integral of density, dV. Right, let's not worry about this constant in here. The negative 4 pi g is a fair multiplicative constant on each side. Why I would want to multiply by that on both sides, don't worry about it. We'll get to that in a second. But for the moment, perfectly legal that I multiply by that on both sides. And really this top line, all it says is mass is a triple integral of density, which is old news. We've known that forever. Okay. All right. Now, why with the negative 4 pi g? And the answer is this. If you consider a certain amount of mass, point mass, keep in mind, that mass, you can write down exactly what the corresponding gravitational field is. Given that gravitational field, you can compute exactly what the corresponding flux is, let's say through a sphere with the center where the mass is. And what is the relationship then of given a certain mass, what is the corresponding flux? Turns out, easy answer, Just write it all down, compute the fluxes. All I'm leaving out is details. This is what that relationship is. This negative 4 pi g is the proportionality constant between the amount of mass and the amount of flux that it creates. So that's just details. And if you want to check those details, if you want to derive this negative 4 pi g for yourself, no problem. Make yourself a little mass, put a little sphere around it. Doesn't even matter how big the sphere is. And you compute the flux, you will get negative 4 pi g times that mass m. Okay. All right. So what else can we say about flux? Well, divergence there. Gravitational flux, aka the flux of the gravitational field. Right? Well, flux is this formula. That's the divergence there. So what this gives us is this nice result here. Right? In some sense, by kind of starting with that and then going around to the left, what we find is that these two integrals are the same, and therefore these two integrands are the same, and therefore we have a relationship between density and the divergence of the gravitational field. Now let me explain why this is a pretty cool result. Let's suppose we had mass distributed throughout space in some complicated way. And I wanted to compute the divergence of the gravitational field, without all this fancy stuff, right? Suppose I just wanted to, let me just write down the gravitational field and take the divergence of it. Well, this is a monstrously difficult problem, because if you have mass distributed across different locations, each little particle of mass, of which there are countless in your distribution, each one creates its own gravitational field. They all have different centers because, well, those pieces of mass are at different locations. So you would have a intractably large number of vector fields that all look kind of like this, but with, shifted based on where the point mass is. You'd have a ton of these things. You'd have to write them all down, add them all up to get your gravitational field. A monstrous formula. And then you'd have to take the divergence of that, right? So it looks like an extremely difficult problem. If you don't use any of this fancy thinking here, very, very difficult problem. And what this fancy work here does for us, it allows us to bypass that whole thing. If you want to compute the divergence of a gravitational field in the vicinity of a distribution of mass, no problem. There it is. Boom. It's this proportionality constant times, well, whatever the mass density is. Simple as that. Pretty cool. Questions? Anybody happy? Okay. You may be thinking to yourself, you're not giving an astronomer or an astronaut, so who cares about gravitational fields, right? Near the surface of the Earth, gravitational fields are constant. Right? Really easy to deal with. Here's why I like gravity as an example. Suppose you want to study electric fields. They too are inverse square radial. So if you want to analyze electric fields, and now this is a much more, real world relatable, engineers constantly having to deal with electric fields, right? They behave just like gravitational fields. Right, so understanding gravitational fields, which frankly I find a little bit more intuitively relatable. We deal with mass all the time. We deal with gravity all the time. I have much better intuition and just sense for matter and for gravity than I do for charges and electric forces, which are so non-visceral, right, in human, sort of natural human life. We didn't even know about them until a couple hundred years ago, right? So this is a much more abstract thing to deal with. It's much harder to get an intuitive sense of what's going on, but they're structurally exactly the same as gravitational fields. So I encourage you, anytime you're looking at electric fields, just think in your mind, it's basically gravitational field. It's just physically different, but it's structurally identical, gravitational fields. Okay, so anyway, I'm going to make the same argument here. We have this stuff called charge. Charge is a count of how many charged particles you have, right? And total charge is an integral of charge density. Of course it is. That's what density means. We can multiply on both sides by this constant. Again, perfectly legal. Multiplying on both sides by a constant is no problem. Why this constant? Well, this constant because if you were to take a given quantity, a given amount of charge, right, a given total charge, if you were to generate its electric field, take a sphere, compute the corresponding flux, what you would find is that relationship is this. And this just happens to be the correct proportionality constant, and that's why I multiplied it into the top equation. Okay, is everybody with me? I'm skipping those details as well. Again, that's physics. Y'all can do that in a physics class. Okay, again, what else can I say about flux? Well, triple integral of divergence. Therefore, these integrals are equal. Therefore, these integrands are equal. And again, then we have a really nice relationship that tells us when I have a distribution of charge, if I know what the charge density is, I don't have to worry about each individual proton and how they're distributed and the individual electric fields being created individually by each one of these things. Oh my gosh, right? I don't have to deal with all of that. All I have to do is take that charge density and multiply by this physical constant, and that'll tell me what the divergence of that electric field is. So an otherwise extremely hard problem turns into an easy problem, ultimately because of the divergence theorem. Okay. All right. Now, quick cultural note: these equations here are called Maxwell's equations. These are. It's tempting to say that this is two of Maxwell's equations. Usually, though, these are referred to as a single of Maxwell's equations. These are thought of as being the same equation, which seems weird. They look totally different, right? So how could we think of these as the same equation? Let me talk through what these equations say, and tell me after I talk through it if it doesn't seem maybe fairly relatable. So this first equation says charge equals flux. Okay. Charge is proportional to flux. There is this constant over here. Charge proportional to flux. Okay. What does this equation over here say? It says charge density is proportional to flux density. Right? I mean, they're basically saying the same thing. This first equation here is saying the relationship between charge and flux locally in terms of densities. And this equation here is giving the relationship between charge and flux globally, thought of as integrals of those densities. Okay, so again, both of these are considered the same equation. I like to number these. Maxwell has 4 equations, each of which has 2 forms. So anyway, these 2 are what I like to call Maxwell's first equation. All right, so that's the last thing I'm going to say about physics related to Gauss's theorem. And let's see here. What was the other? Yeah. Anyway, we'll have more to say about this. So related to this physics, just a real quick note about courses here at Duke. If you've already taken an E&M course like Physics 152, I think it is, you might think back to all of that stuff and ask yourself if this doesn't maybe make some of that make a little bit more sense. Very often in a physics class, they will talk about these equations, but maybe not show the relationship between them, maybe not motivate the connection between them, because they can't assume you know the divergence theorem, etc. Right? Knowing the divergence theorem, this gives you a stronger connection. If you have not yet taken an E&M course, when you do, think about this. Right? This will help a lot. All right, so moving along. Back to the beginning of section 7.3. Remember, the book does these in a different order than I'm doing them. The book starts with Stokes' theorem. I think it's a little weird. Whatever. Okay, so we have another theorem. It's going to be just like a lot of the other theorems we've already talked about. Notice, structurally, we're going to start by talking about boundaries and orientations. Then I'm going to talk about accumulation. Then I'm going to talk about densities. It's the same order of ideas that I have done with all of these previous accumulation theorems that we've talked about, aka density theorems, aka boundary theorems. So, reminder, the reason I do this, it's not because individually these are necessarily the best or the quickest ways to get to the results of these individual theorems. It's that the theorems have a lot in common, and I like to motivate them, however you want to say it, in ways that are perfectly analogous as much as possible to emphasize how closely related they are to each other. Right? That's part of my intent in this course. So, all right, let's talk about boundaries. We're going to think about surfaces in space. So imagine some kind of like this, right? Some surface floating up in space. For that surface, we can talk about the boundary curve of that surface. Now, here's the boundary curve. No problem, except for one thing, and that is remember at this point of the course, all the vector calculus we're going to do, everything needs to be oriented. All surfaces are oriented surfaces. All curves are oriented curves. So the question becomes then, if I have an oriented surface, not just a surface. So my surface comes with an orientation, namely a choice of normal vector there, making this an oriented surface. What is the resulting, what we call induced orientation on the boundary curve? Should the boundary curve be thought of as going that way, or should it be thought of as going this way? It needs to be an oriented thing. What is the orientation? Right? And remember, we've already addressed this question for certain circumstances. When you're talking about a two-dimensional region in R2, we have this rule about, move in such a way that the regions on your left tends to work out to be counterclockwise, most of the time, exceptions granted. Then we have, for solid three-dimensional things, the boundary is a surface, with the understanding that the orientation is, again, arbitrary convention, away from the solid. Arbitrary. Okay, well, what about this boundary? I need an induced orientation on this boundary. Here's the rule. It is arbitrary. Correction, it was arbitrary 150 years ago when this was getting worked out and settled. But now that choices have been made, right? A la electrons are negatively charged, protons are positively charged. That was an arbitrary choice a couple hundred years ago. At this point, not arbitrary. It's convention, it's standard, and it's not optional. Likewise, here's the rule. Right hand, thumb in the direction of your surface orientation vector. Look at the fingers of your right hand and notice that your fingers point around the thumb in a certain direction, defining what I like to call a swirl. The swirl here, that swirl will sideswipe up against the boundary in a certain direction. Let's see. Let me use orange, I guess. The direction that the swirl sideswipes up against the boundary, that is the direction of the orientation on the boundary curve. It's an arbitrary choice. Thumb in the direction of the normal, fingers define a swirl, the swirls sideswipe to create a tangent direction on the boundary curve. Is everybody happy with that? Any questions? Okay. Make sure to use your right hand. It matters. Okay. Alrighty. Okay, moving along. Accumulation. So, big surprise, we're going to find an accumulating quantity here. After all of our accumulation theorems are about accumulating quantities, thus the name. So, here's the accumulating quantity. It's boundary circulation again, just like with Green's theorem. Same quantity. Slightly different context. Now keep in mind, Green's theorem was in 2 dimensions. We had a 2-dimensional region with a boundary curve in the XY plane. Right? Here we have a surface floating up in space with a boundary curve that is also a curve in space. Right? But it is still an oriented curve. We can still therefore talk about boundary circulation, and for reasons that are really not that different than what we've seen before in the Green's theorem context, boundary circulation does accumulate. Now, I'm going to draw the pictures, but I'm going to go through this relatively quickly because it's really very much the same as what we've talked about before. Here we go. If I were looking at this half, if you will, of the surface that I'm looking at, and with the understanding that it's oriented as indicated, thumb and swirl and side swipe, etc. Whoops. Then I get this as the how I would represent the boundary circulation on S1. Now let's look at S2, this piece on the right here. Here we have, again, a piece of surface. Again, it needs to be oriented. Oriented, of course, consistently with the way the S1 is oriented, right? They have to kind of, have to be the same, as it were. And that boundary circulation be represented like this. Right, so I've got a boundary circulation on the left, I've got a boundary circulation on the right. Here's the boundary circulation for the whole now, looking at the whole thing. Boundary circulation would be like this. So is green plus blue equal to purple? Well, there's a lot of overlap. A lot of the green follows the purple. A lot of the blue follows the purple. There is the sticky wicket, though, that after I've accounted for where they sort of track each other perfectly, there is this leftover. Right? What we have, this green and this blue together seem to be the difference. This is our problem, in other words. And the thing is, notice these are both along the same curve, but with opposite orientations. So these 2 line integrals are exact negatives, which then cancel. And we are left with the whole being exactly equal to the sum of the parts, and so boundary circulation accumulates. Okay, how are we doing? Does that all make sense? Hope also, does that look familiar? You'll notice the picture is actually extremely similar to the picture that we drew for Green's theorem, where we were also looking at boundary circulation. The only difference is this is in space instead of in the plane. Okay. So once you know it's an accumulating quantity, the rest of the ideas follow along exactly the same way as previously. So, again, you can talk about, for a whole surface, you can talk about boundary circulation, which of course we visualize as being on the boundary, but it is literally an accumulation over the interior. You can think of circulation, and therefore you really should think of circulation as being distributed across the interior. Because, again, look at the algebra. That circulation is equal to a sum of a bunch of circulations that look like this. Right? And if you were to add up over the whole surface, the sum of all those little greens gives you the purple. The circulation is literally distributed over the surface. So let's think of it that way. And if we're thinking of circulation as being distributed over the surface, we can talk about density. If I think again of circulation as being something that is in each little piece of surface, then I can talk about how much of that there is per unit area. And correspondingly talk about circulation density. And it's just like with Green's theorem. Same ideas. Just 3-dimensional instead of 2. But still circulation per unit area. How are we doing? Is everybody on board? Is everybody with me? Does anybody have any concerns about this being in 3 dimensions instead of 2? Anything like that? Okay. So, good news. This can be computed. More good news. We're not going to. In this class. It's a bunch of details. They're not that interesting, really. I mean, it's an important calculation in the sense that we're going to do very important things with this result. But the calculation itself is I think of it as a technicality. I think of far more important than knowing that this is a formula we're going to do something with is understanding how to think about it, and in particular that it represents circulation per unit area. That's, I think, by far the more important thing. Okay, so that said, we're basically ready to write down our theorem. I do want to make one observation that is a little bit uncomfortable. This expression clearly depends on the vector field. Well, of course it does. Look at every other density that we've talked about. The derivative depends on the function whose change you're looking at. Green's operator is an explicit formula computed on the vector field. Divergence is an explicit formula computed on the vector field. Here's what's weird. This density also depends on the surface. Depends in particular on what this normal vector is. It depends on how that little piece of surface is arranged in space. Right? So how that piece of surface is arranged changes what our circulation density is. So that's a little weird. It's a little creepy. It's going to turn out to be no problem. And I am going to come back and talk about this more later. For the moment, I just wanted to plant the observation that this is an eyebrow raiser. It's a little bit of a concern, and we will make sense out of it later. Okay, so here's the theorem. Putting it all together. Again, we've already got all the pieces. We just have to snap them in place. Circulation is a quantity. It's an object of interest. I can give it a name. I'm calling it with the little lowercase Greek letter sigma there. As a quantity, it accumulates the sum of the parts. Right? Second thing that we talked about earlier. And then furthermore, there is an associated density. Namely, there is a quantity that I multiply by area. Let's say that differently. There's a quantity that I can multiply size to get circulation. And of course, we call this density circulation density. So circulation per unit area times area gives you circulation. And now, right before we actually finalize this is a notational point, and this is somewhat satisfying to our previous concern. We were looking at this little n vector and concerned about what's it doing there. Isn't that going to kind of mess things up, and isn't that a little weird? Notice, though, that little n, now that we multiply by ds, scalar, this is exactly how we have previously written the ds vector. So that actually kind of nice. That actually fits kind of conveniently. So all together then, here is our theorem. This is referred to as Stokes' curl theorem. And there it is. As a computational tool, the point is, if you're looking at a line integral, hey, you might be able to use this theorem to instead instead of brute force computing the line integral, you can write down a flux integral that's got the same value, and it might end up being computationally easier. Okay, so very similar in how it looks at a glance, anyway. Very similar to Green's theorem, right? Which was about a line integral that was computed with a double integral. Here we have a line integral computed with a flux. Everybody all right? Okay. There's always a catch. All these boundary theorems have catches. Here again, you could probably see this coming. Just like with Green's theorem, the catch is that this will not compute just any old line integral. As is explicitly noted in the statement here of the theorem, it's got to be a boundary line integral. Specifically, in other words, a boundary circulation. That's a strict rule. Couple ways to say this. For one thing, it's only if it's a boundary that the argument works that we've just made, right? Because it was explicitly boundary circulation that we argued would accumulate over a surface. But furthermore, more bluntly, anyway, if your curve is not a boundary, then there is no surface for it to be the boundary of, right? If it's not a boundary, then it's not the boundary of a surface. And if it's not the boundary of a surface, then there is no surface over here over which to even talk about a flux integral. So it's not that Stokes' theorem doesn't work for non-boundaries. It's that there is no Stokes' theorem. It doesn't have a chance to work because there is no right-hand side of the equation. So only for boundaries. Cannot emphasize that enough. Be real careful with that. And we'll talk more about that later. Okay, let's get a win under our belts. Here is an example. Notice the question here asks us to compute a line integral, and we have a vector field given, and we have a curve given. So given a curve and a vector field, compute the line integral, no problem. Now notice in the statement of the question here, doesn't say anything about the curve being a boundary. Notice also in the question here, it doesn't say anything about using Stokes' theorem. Right? So that one thing y'all have to keep in mind when you're working, exam questions, homework questions, you've got to look at the situation and decide for yourself what an appropriate tool might be. When you're looking at a line integral, let's just count options here. A line integral in 3 space. Fundamental theorem of line integrals would be something worth trying. Maybe, possibly, depends on the details. There's particulars to be considered. Stokes' theorem is the other option that we might consider. And of course, don't forget, it might be that neither one of those applies, and you might have to actually pull back through the parameterization. That is also a possibility depending on which particulars work out and don't work out. So, anyways, keep that in mind. Don't just rely on the kind of the visual cues in the question. In fact, if you look at the statement of this question, the curve is given parametrized, right? I have an explicit parametrization given. If you were to rely on the kind of the subtext of the statement of the question to guide you on what approach to take, well, the curve is given parameterized. You might take this as a suggestion that you should answer this question by parameterizing and pulling back through the parameterization. And it's not that you can't, but that would certainly be a harder way to solve this problem. Okay, so what we're going to do is think about this curve. We got this curve C, again parameterized like so. I can draw a picture of it. After all, notice that x squared plus y squared is equal to 1. Z is equal to 0. And in fact, the only thing distinguishing this curve from our usual sort of just, cosine comma sine, right? I mean, the most basic parametric circle we have, the only difference is that we're that one minus sign right there. Right? The y coordinate is the negative of what our sort of more familiar circle would be. So in other words, it's a reflection across that line, reflection across the x-axis in the xy plane of our more familiar circle. Everybody with me? Okay. 0 to 2 pi means it goes all the way around. Okay, so what else can we say about this curve? Again, we get an orientation here. Let's see. You know what? Let me write this a little bit more visibly. I'm going to do this in a pen. There we go. Okay, there's our orientation. Our curve, what you might call clockwise as seen from above. Why clockwise? Well, because this is a reflection of our more familiar one, which we already know is counterclockwise as seen from above. Okay. All right. Is this a boundary? Why, yes, it is. Easy to see. This curve is a boundary of that surface. Lovely. Now, wait a minute. Let's worry about orientations. Could it be that this is not a boundary because I need it to go the other way or something like that? We've seen that kind of thing come up in doing problems with Green's theorem. The good news here is we don't really have to worry about that. We just have to infer what the orientation is on the surface whose boundary we're looking at. I like to call this surface the anti-boundary, by the way. I just find that convenient. So how do we find the proper orientation on our anti-boundary? And the kind of a trial and error is the answer here. Keep in mind, I have rules. Oh, here we go. I have rules for given a surface orientation, what the corresponding boundary curve orientation is. We just need to turn that around backwards. And given a boundary orientation, I need to figure out what is the corresponding surface orientation. And what I like to do is just trial and error. There's only two options. It's either this one or that one. Just try them, right? If you guess right, cool. If you guess wrong, you kind of already know that it has to be the other one. So it's pretty hard to complain about in terms of convenience. So let's deliberately try the wrong one just so we can see how it fails. Let's suppose that our surface here were oriented that way. And if it were, then thumb in that direction and fingers of my right hand defining a swirl. The swirl would go like this, which would sideswipe up against the boundary like that. And notice it's just the wrong way. That's it. This is not the orientation that gives rise to what I need. My curve is explicitly given with this dark blue orientation. That speculated upward orientation on the surface gives me the opposite, aka the wrong orientation. So it wasn't that one. That means we know the right answer pretty automatically right now, but let's check it anyway. Let's try the downward orientation on my surface. Downward, thumb of your right hand, fingers of your right hand defining a swirl, which has your orientation going, your induced orientation going that way, and that is the correct induced orientation on our curve. How are we doing? Everybody follow that? Everybody see why you kind of have to just trial and error? Right? And it's really not that bad. There's only two choices. So.
If the parameterization isn't a circle, how do you know which way it goes?
So that when you write down a parameterization, you can also write down the corresponding velocity, and velocities are always in the direction of the orientation. So a parameterized curve is naturally, automatically oriented by way of its velocity vector. Does that make sense? Yeah. So if you were to write, you could literally compute x prime here, right? And wherever you might happen to be on this curve, x prime would be a formula. You could write down the exact velocity vector. What you'd find is that they all point kind of what you might call clockwise, going around this circle. Does that make sense?
Yeah.
Yeah.
So you see the derivative of each of those with respect to t?
Yep.
Okay.
Yep.
But how would sine t negative cosine t 0 tell you that it's...
Well, you can just plot those. I mean, so let's
as t
yeah, just plug in like t equals 0, for example, and that's going to give you a velocity vector at the point t equals. Let's just do it. Let's consider t equals 0. Where t equals 0, we're at 1, 0. That has us right there. Let's compute x prime. X prime is let's see here, negative sine t, comma negative cosine t, comma 0, which when you plug in t equals 0 gives us 0, negative 1, 0. And you see that's clockwise.
Yeah. Okay.
Yeah. Yep. How we doing? Everybody all right? Okay, so we're almost done with this example. Let's see. Yeah, we've realized our curve as a boundary. Let me write this again. Let's see. So here's our curve. Is the boundary of this surface oriented downward, and which means, by the way, that of course it's 0, 0, negative 1, because I do know that this is a horizontally flat surface, so the normal vector is either straight up or straight down. We've agreed it's downward, so it's got to be 0, 0, negative 1. And now it's just a matter of plugging in. Here's the Stokes' curl theorem, right there, applied to our given curve, which is a boundary. The curl is just a matter of computing. You can take the given vector field up here and explicitly compute the curl. Let me color code that better. Explicitly compute the curl of that vector field. A little tedious, right? You got to take various partials, and it's that whole symbolic determinant thing. Make sure that you are reliably, comfortably, proficiently able to compute curls. It's going to come up. Right? So we're going to make sure that that's nice and quick. The curl turns out to be 0, 0, 2, as it happens. The normal vector we just agreed is 0, 0, negative 1. And that leaves us with our integrand being a constant. This is an integral over a garden variety surface, namely a disk of radius 1, I guess it was. And so easy geometry, and there's our answer, minus 2 pi. How we doing? Ready to follow all that? All right. Okay, so real quick, let's see, I have a minute and a half. I just want to remind y'all, we've already actually seen the circumstance that I got all fretty about earlier, namely, what do we do with the fact that our density has a vector in it that depends on the orientation of the surface, and oh my gosh, that seems all creepy and weird and unfamiliar. Not at all. Here's the fundamental theorem of line integrals. The density, as we previously discussed, was gradient dot t. It also depended on the orientation of the curve. Right? So we're actually in a very familiar circumstance. What I want to point out is that we had a sort of an approach for dealing with that at the time, and the approach was to say, well, let's just kind of combine it with the ds, call that the x. We'll think of this as an oriented size, kind of, if you will, right? I mean, dx tells you by virtue of its magnitude, it tells you what that size ds is, but dx also tells you the direction. This gives you orientation and size. So I like to think of it in my mind as oriented size. And how do I relate a quantity to an oriented size? Well, I would call that an oriented density. And I did back in chapter 6. Because the quantity in question is change, I call this the gradient. I call it oriented change density. Another point of view, another way to think about this, if you look at the gradient itself, it is telling you two things. By virtue of its magnitude, it's telling you how steep the mountain is. It's telling you how much change per unit distance there is. Uphill, of course, right? In the direction where the change is actually happening, of course. And then it also tells you what direction that change is maximally happening. Right? So again, natural reason to call it oriented change density. The direction is the orientation in which the change density is happening. All right, so I'm going to draw the line right there. What we're going to find on Friday is that, Wednesday. What we're going to find on Wednesday is that there's a very analogous point of view on curl. We will talk about that on Wednesday. Y'all have a good one. See you later.